Thank you. Welcome, everyone. So this talk today is by Amirali Ahmadi. He's a professor at Princeton in the Department of Operations Research and Financial Engineering. He also has a number of affiliate positions in computer science, statistics, aerospace, mechanical engineering. There's a long list. Okay. He's a big shot at Princeton. Right. So Amirali received his PhD from MIT, from EECS. And then he was a Goldstein Fellow at IBM Watson after that. And he has a whole number of awards, including the Sloan Presidential Early Career Award for Scientists and Engineers, the PCASE, the NSF Career, AFOSR Young Investigator Award, DARPA Faculty Award, and so on and on. So it's many, many awards. Amirali has won several teaching awards as well at Princeton. And I think we're in for a treat. Okay.
Yeah. So thank you, Reka, for the invitation, and all of you for coming here today. I want to talk about the complexity of finding local minima in polynomial optimization. And this is joint work with a former PhD student, Jeffrey Zhang, who's now at Yale. And if I have maybe 5 to 10 minutes left at the end, I want to tell you a little bit about a more recent project on designing higher order analogs of Newton's method, and there's a nice connection between that and the problem of finding local minima of polynomials. Okay, so the picture, and this talk is quite high level, and feel free to stop me and ask questions at any point. The picture I would like to have in mind as a motivation for this talk is some landscape like this, when you have a non-convex optimization problem, so there's a distinction between local and global minima. And I want to, at a high level, study this question, that if we're in a situation where global minima are hard to find, can we at least find a local minimum efficiently? And I want to formalize what this means. But in fact, this is the intuition that a lot of practitioners of optimization have. You know, when they have a non-convex problem, they have some sort of descent method, let's say gradient descent or some variant of it. And they think that they may not be finding the global minimum, but their algorithm could be getting stuck or getting trapped in a local min. And I want to see if this is actually what happens for a class of problems that I think is insightful to look at. Okay. So let me now formalize this. Let me define what is a local minimum. So let me also do it in the constraint case. So you have an objective function f and a feasible set omega. And a point, a member of the feasible set, is a local minimum if there exists some positive radius, delta, such that if I look at the neighbors of x bar within the radius delta that are also feasible, then x bar is better in objective value than these neighbors, or at least is no worse. Right? And delta is allowed to be as small as you want. It just has to be positive. So for this toy univariate example, f has 3 local minima, these 2 in the interior, and this one on the boundary, because comparing to the feasible neighbors, this point on the boundary is better in objective value. Now, if I want to talk about the complexity of finding a local minimum, I have to tell you how f and omega are represented. And for this talk, I want to focus on the case where the objective function is a multivariate polynomial, and the feasible set is a basic semi-algebraic set, so it's a set defined by finitely many polynomial inequalities. I claim that this is a reasonable setting to look at because polynomials on compact sets are dense in the space of continuous functions. So for a local notion like local minimum, it makes sense to look at polynomials. Also, several problems that we see in optimization, they're naturally either defined by polynomials or they're approximated by Taylor expansion to bring us in this setting. And moreover, I want to study the complexity of this question in the so-called Turing model of computation, where the input needs to be given to me with a finite number of bits. So if I have a polynomial optimization problem, the input would be all the coefficients that define the objective and the constraint functions, and I take them to be rational numbers. So all of the input then is a list of rational numbers. The size of the input is the number of bits I need to write down all these rational numbers. And then I can talk about, what's the best algorithm, what's the running time of the fastest algorithm as a function of this size of the input that can find a local minimum. And I don't care which, if you have multiple local minima, I'll be happy if you return to me any one of them. Okay? Any questions about the setup? So I have as input description of f and omega given as coefficients of some multivariate polynomials. And I want to ask, does the problem have a local minimum? And if so, ideally, I want the algorithm to return me one. So let's look at some basic cases. So if omega is polyhedral, so all the GIs are affine, and f is a linear function, this is, of course, linear programming is a convex problem, and local and global minima are the same and can be found in polynomial time. So for instance, by ellipsoids method. Right? So then the next case is where I keep the degrees of the GIs equal to 1. So omega is still a polyhedron. But I increase the degree of f just by 1. And now f is a quadratic function. And this is called quadratic programming. And already in the 90s, it was known that finding global minima now is NP hard, even if the quadratic function has a single negative eigenvalue. But the question I want to look at is about what about local minima? Like this is the first interesting case now that there's a distinction between global and local, and I want to understand if it's any easier to find local minima. In fact, we were not the first to ask this question. This question appears explicitly on this nice paper by Pardalos and Vavasis. So in 92, they collected 7 problems that they presented as a list of 7 interesting questions in complexity theory for numerical optimization. And this is problem number 3. It's exactly asking what is the complexity of finding even a local minimizer for a non-convex quadratic program, assuming the feasible set is compact. And I'll tell you on the next slide why they require compactness of the feasible set. But on this slide, I want to make a distinction between a related problem that is also mentioned here, in case some of you are familiar, which is the recognition problem. So in this talk, I'm interested in 2 related questions. One is, given the data of an optimization problem, tell me if there's a local min, and if so, give me one. So this is what I call the search problem, the search for a local min. But it's a related question of the recognition of a local min, which means that I'm given as input f and omega, and a given candidate, a point x in Rn, and I'm asked, is this point a local min, yes or no? Can I recognize local minima? And it was already proven by Morty and Ahmadi in an influential paper that this is NP hard for quadratic programs. But as the question suggests here, this does not rule out the possibility that there could be another point that you can find easily and verify to be a local minimizer. So to make this distinction concrete, let me just tell you how Morty and Ahmadi proved this result. So if you believe that checking whether a matrix is copositive is NPR, then this is a one-line reduction. So a symmetric matrix M is copositive if its quadratic form is non-negative over the non-negative orthant. So that's an NPR property to check. Now, suppose now I consider the problem of minimizing x transpose mx, that's the quadratic function, over the non-negative orthant, which is a polyhedron. I claim that the origin is a local minimum if and only if m is copositive. Well, if m is copositive, then the quadratic function vanishes at the origin and is non-negative everywhere else. So 0 is, in fact, a global min. Now, conversely, if m is not copositive, that means that there is a vector x hat in the non-negative orthant where this quadratic form is negative. So then I can draw the line to the origin, and by homogeneity, the objective will be negative on the entire line. So that means that 0 is not a local min, because there's a descent direction in the direction of x hat. Right? So this shows that recognizing a local min is hard, but this reduction fails for the problem that I'm interested in, which is the analogous would be, is it true that a matrix is copositive if and only if this problem of minimizing a quadratic function over the non-negative orthant has a local min? And this fails because it's possible to have non-copositive matrices, such as this one, which is clearly not copositive because of this diagonal entry, but still have local minima. So in this case, there is another local minimum that pops up somewhere else at the point 1, 0. So this reduction fails. OK, so I hope there is. The main message is that there are 2 related problems. One is recognizing whether a given point is a local min, And one is just given the data of the optimization problem, can you find the local min? OK, and the reason that the question requires the feasible set to be compact is that when the feasible set is compact, then there is clearly at least one local minimum, namely the global minimum, right? And moreover, it was known already in the 90s that for quadratic programming, there's always a local min, in particular the global min, which is rational if the input is rational and has polynomial bit size. So if you've seen like the problem of finding a Nash equilibrium in a two-player game, this is a similar situation where a Nash equilibrium of polynomial size always exists, but the question of finding one could be hard. So meaning that for quadratic programming, there is always a nice local minimum that can be represented with few bits. But the question that these guys were asking is there an algorithm that can find it? Right? So here's the main theorem with the first paper with Jeff. So we showed that unless P equals MP, there cannot be a polytime algorithm that finds a local min of a quadratic program. In fact, the result is even more negative. There cannot be a polytime algorithm that gets even exponentially close to any of the local minima. So think of any constant c. So c, let's fix it to be 2. There can be a polytime algorithm that gets within Euclidean distance 2 to the n of some local minimum of a quadratic polynomial over a polytope, where n is the number of variables. Any questions about the setup or the statement? OK, so I will not be able to completely prove this. And again, this talk has only maybe one simple proof later. But let me tell you like what is the outline and what are some elements that go into this proof. So like any other NP-hardness proof is done by reduction. So usually you start with some discrete combinatorial problem and show that if you could solve this problem, you could also solve that discrete NP-hard problem. And in this case, where we start with is the problem of finding the largest stable set in a graph. So let me remind you, if you have a graph G, a stable set in a graph is a subset of the nodes that are pairwise disjoint. So for any two of them, there is no edge connecting them. So for instance, these 5 red nodes form a stable set because you can't see an edge between any two of them. And the size of the largest stable set in a graph is denoted by alpha. So in this graph, alpha is at least 5. And you can verify that there's no stable set of size 6, so alpha is exactly 5. And the decision problem, which is well known to be NP-hard, this is one of the first 21 problems shown by Karp to be NP-hard, is given a graph G on n nodes and a threshold integer r between 1 and n. Tell me if there is a stable set of size r, or at least r. These are the same question. OK, and so what we show in the paper is that if there was a polytime algorithm that gets within distance c to the n of any of the local minima of the following quadratic program, we could decide if given a graph there's a stable set of size r in polytime. And what is this quadratic program? So the reduction is actually just fits on half a page. So you carry, so the graph goes into the objective function. A is the adjacency matrix of the graph. I is the identity, and J is the matrix of all ones. And R is this threshold. You're asking, does the graph have a stable set of size r? And for some technical reasons, you need to subtract the threshold here. So r is, 0 wouldn't work, but any other constant is OK. And the feasible set is the convex hull of essentially some scaled version of the simplex and the origin. So it's compact as required by Pardalos and Vavasis. So this is the feasible set. Right? And this reduction takes polytime. Now you can trust me that you can compute the ceiling of this quantity in polynomial time. And some of you who've worked on reductions may be concerned that I have c to the n in my reduction. But I remind you that the number of bits you need to write down c to the n is log of c to the n, which is n. And I already have n squared numbers in the matrix A. So this is indeed a polytime reduction. You're allowed to write down this number in polytime. Or you can write down that number in polytime. Okay. So why does this work? again, that's the part that I'm skipping. But what we prove in the paper is the following, is that if you write down this quadratic program, we can actually analyze where its local minima are going to be depending on whether the graph had this large stable set, meaning there is a stable set of size R, or it didn't, meaning all stable sets have size less than R. Now, if all stable sets are small or less than R, then we can show that there's only a single local minimum for this problem, and that's at the origin. If there are large stable sets, then there could be multiple local minima, but all of them will be on this hyperplane, meaning they will saturate the last constraint. So this is what I'm not proving. But if you believe these two claims, then the theorem follows, because suppose there was a polytime algorithm that, given any quadratic program, would land within distance c to the n of one of its local minima. Well, take your algorithm and just apply it to these quadratic programs. Now, because the algorithm guarantees to land within distance c to the n, and OK, so the distance from the origin to this hyperplane, you can compute it to be 3 times c to the n. That's how this constant is picked, right? So if your algorithm always lands within distance c to the n, is never going to land in the white region. Is either going to end up in the blue region or in the orange region. But I can run the algorithm and see where it lands. And if it ends up in the blue region, I know that the local min must be at the origin, which means alpha is less than R. If it lands in the orange region, I know that the local min must be on the hyperplane, which means that alpha is more than or equal to R. So that allows me to solve the stable set problem. I know this is high level, but any questions? All right, so before I move on, I just want to tell you an implication of this, which, at least to us at the time or to some practitioners could be counterintuitive, is that, so here, so the claim is that now pick any polytime algorithm that attempts to find a local minimum. So for instance, let's think of a concrete algorithm. Maybe I do gradient descent on a quadratic with a certain step size, maybe the 1 over k step size. And I take a step, and if it leaves the feasible set, I project back to the polytope. So projection to a polytope is efficient, and let's say I run this for n to the 100 steps. So now I have a fixed polytime algorithm. And the question is, does it find the local minimum of a quadratic program? And unless p equals np, so if you look at all qp instances that can be encoded with k bits, so there's 2 to the k such instances. So your algorithm is going to fail, meaning it's going to land exponentially far from any local minima on a number of instances that cannot be bounded by any polynomial in k. So the number of bad instances must be super polynomial in k for any algorithm. So I just fixed one algorithm, but you could have fixed another one, right? So going back to my beginning slides, it's the intuition that local minima are easier to find, at least for quadratic programs, is incorrect, at least in this sense of complexity. And even getting close to local minima could be as hard as finding global ones. Yes?
So why is that true? So that
this claim?
Yeah.
This follows from these papers in complexity theory, and is nothing specific to the local min here. This is true for any NP-hard problem. There are some nice results that limit the power of heuristics on any NP-hard problem. So they show that not only they must fail on some instances, that any fixed algorithm must fail on super polynomially many instances. So it follows, there's a nice survey paper by Ryan Williams at MIT that reviews all these results. And I'm just applying that to, is the same claim is true about the stable set in a graph or your favorite NP-complete problem, right? I'm just applying it to this problem. It is not obvious at all. It's just from NP hardness why this follows. OK, so now, so the next part of the talk will be a little bit of more of a positive message. But let's go back to the picture I had on the first slide, in which I had no constraints. Now, if I've already shown you that if you have a quadratic objective function and linear constraints, you cannot find local minima. You cannot even get close to them, right? So that means that, and the constraints don't get any simpler than polyhedra, right? So that means that the other cases of polynomial optimization can only be harder than this. So the only chance I have for efficiently finding local minima, at least in the setting of polynomial optimization, is if I have no constraints. So now I want to move to the unconstrained case. So the question is even simpler to describe. It's given a polynomial of degree d, meaning given its coefficients as input, can we test if he has a local minimum? And if so, can we find one efficiently? And I want to study the complexity of this question for different values of the degree. Now, if the degree is 4, with Jeff, this is in the same paper, in fact, we showed that this problem is strongly NP-hard. In fact, this is a key lemma that goes into the proof of the previous fact I proved. There's a nice connection between degree 4 even polynomials and quadratic programming. So that claim is almost half of the proof of what I presented previously. So I'm not going into it. Now, if the degree is 2, this is classical. So if I have a quadratic polynomial, I can check if he has a local min in polytime. All I have to do is to set the gradient equal to 0. That gives me a system of linear equations. I solve a linear system in polytime. And I check. So if he has no solution, then there's no local min. If I have my hand on any solution, I just check if the Hessian is positive semidefinite. I can do that at polytime. If both answers are yes, I have a local min. Otherwise, I don't. So basically, linear algebra solves the degree 2 case. So in the literature, the middle case had remained open. So that's the case of degree 3. And it turns out degree 3 is actually extremely interesting. There's a lot of nice algebra and geometry that arises in degree 3. So just to give you an intuition of why degree 3 is more complex than degree 2, let's look at this example. This is a cubic polynomial in 2 variables. I'm plotting his level sets in x1, x2 space. And I'm showing you where the polynomial is positive. So it's positive over above this parabola and is negative in between. And now let's look at the origin and think together if origin is a local minimum. Right? So if I'm sitting at the origin and I'm looking in any line along any direction, then I claim that I will see the function immediately increasing. Right? So this is clear. If I look down, the function is increasing. If I look up, the function is increasing. But even if I look diagonally, before I move to the negative region, there will be some part where I first go positive. So what this means that across any line I am increasing, there is no descent direction. And this may fool me into thinking that the origin is a local min. But the origin is not a local min because there is no descent direction, but there is a descent parabola. So there's a parabola, this red one, that if I move along the parabola, I will immediately decrease the function. So the origin is not a local min. And this behavior does not happen for quadratics. If a point is not a local min of a quadratic, there is always a descent direction that certifies it. So hopefully this should tell you that it's not clear if we can even recognize if a given point is a local min. So let me first focus on the recognition problem. So it turns out that we can. So a point z in Rn is a local min of a cubic polynomial if and only if 3 conditions hold. Now, you all recognize the first 2 from your first nonlinear programming course. These are the first order and second order necessary conditions. The gradient should vanish, and the Hessian should be positive semidefinite. But there's a third condition that's needed. We call it the third order condition, which is that if you have any vector in the null space of the Hessian evaluated at your candidate point z, then the gradient of P3, which is the top homogeneous component of P, should vanish at this point. So what is P3? So you have a polynomial P of degree 3. It has monomials of degree 3, of degree 2, degree 1, degree 0. So P3 is just the top homogeneous part, is all the monomials of degree 3, exactly 3, and their coefficients. So you take that homogeneous cubic, you take its gradient, and that vector should vanish if you plug in, that gradient should vanish if you plug in any vector d in the null space of the Hessian. So this is an exact characterization of local minima, and moreover, these conditions can be checked in polynomial time. And I'll argue why in a couple of slides. I guess I'm not going to prove this, but I have some intuition as to where this third condition is coming from. So I claim that it's easier to see that the following is a necessary condition, where I have the same implication except I drop the gradient. So I'm saying if D is in the null space of the Hessian, then the top homogeneous component of the polynomial should vanish. So this is necessary because let's say I have a point x bar. So this is a two-dimensional picture, but this could be an Rn. I'm checking if x bar is a local min. I have a direction D, which is in the null space of the Hessian. So if I just look at this restriction, this univariate restriction of the polynomial where I start at x bar and I look at in the direction D, that univariate polynomial should look like this because the quadratic term of the Taylor expansion is vanishing because D is in the null space. And the linear term vanishes because the gradient is 0. So that univariate thing looks either like x cubed plus a constant or minus x cubed plus a constant. So that means that if P3 is non-zero, either I can decrease by moving left or right. So that cannot, if this condition is violated, I'm not a local min. However, this condition only rules out descent directions. It doesn't rule out descent parabola. And we've already seen that you also need to rule out descent parabola. So it turns out that when you require the gradient to vanish instead of P3, that's a stronger condition. So for a homogeneous function, if the gradient vanishes, then the function vanishes. You can see this from Euler's identity, for instance. And this stronger condition turns out to also rule out descent parabola. So that's just some intuition. And why can we check these three conditions in polytime? Well, first and second order, again, this is basic linear algebra. How would you check the third condition, that on the null space of the Hessian, some gradient vanishes? So you can compute the basis for the null space of the Hessian at your candidate point. You can find the basis in polytime by solving, say, some linear systems. So let's say K is the dimension of this null space. And then I have the top homogeneous component of P. So I have the coefficients of that term. I can take the gradient. This is now the elements of the gradient are quadratic forms. And I need to check whether n quadratic forms vanish on a null space. So any point in the null space would be of this form. And these quadratic functions would vanish everywhere if and only if all their coefficients are 0. So these are now quadratic functions in alpha, and I can check whether all the coefficients are 0. So yes?
So presumably something goes wrong if we try to extend this to the fourth order. So I guess I'm just curious.
Certainly. So in fact, in the paper, we have examples that show this last condition is neither necessary nor sufficient for fourth order polynomials. It's clear that it's not sufficient. Necessary, we have a nice example. What happens is that in the fourth order, you need to also worry about zeros of the third order tensor and have a condition on the fourth order term, what it's doing on the zeroth of the third order tensor. And that is intractable to check because we already know it's NPR to recognize. Yeah. So yeah, really 3 is the last tractable case. For degree 4 is NPR to recognize local minima. So the geometric and algebraic conditions, one can write more complicated conditions, but they will no longer be tractable to check. But now let's go back to the main question I was after. I didn't want to just recognize if a given point is a local min. That's a nice first step. What I really wanted to do was to find local minima, given just the coefficients of a cubic polynomial. Right? So the question I want to ask is that if you give me the coefficients of a cubic polynomial, can I tell you if he has a local min or not? And if so, can I return one? So let's start with a quote-unquote simpler question. So can we even find a critical point? So a point where the gradient vanishes. And why do I say this is simpler is, when we teach nonlinear optimization and we ask students to find local minima, the recipe is usually set the gradient to 0, right? Find your critical points, and then check the Hessian, whether they're PSD or not, and continue. So it's always the first step is to find critical points. And we showed that, and I'm going to prove this. This is easy to prove, that in fact finding a critical point of a cubic polynomial is an intractable task. So more formally, testing if a cubic has a critical point is strongly NP hard. However, somewhat surprisingly, at least to us, you can find the local minimum of a cubic polynomial by semidefinite programming. And this is not a hierarchy of STPs or anything. It's just a fixed set of semidefinite programs that have STP blocks that are n by n. N is the number of variables. And in worst case, you need to solve like 2n STPs, 2n STPs of size n. Right? So I find this interesting because it shows you that the right way of finding local minima is not to first find critical points. In fact, that would be NP hard. But the right way is to bypass the step of finding local minima, the step of finding critical points and directly search for local minima. So let me tell you why these two claims are true. And again, the first claim I can prove formally, and the second claim is the main result of this paper. And it takes much more work to prove, but I will try to give some intuition. Yes?
Just comparing those two results by
Yeah.
eye.
Yeah.
Like, if you find a local minimum, would that not help you to decide if a cubic polynomial has a critical point?
Good question. I get that question often. So if you so you see, when you have two properties, the one implies the other. In this case, local min implies critical point, but not the other way. If I know the complexity of one, I don't know anything about the complexity of the other. So in this case, this happens because if I find the local min, then sure, that's a critical point. But what if this says there is no local min? There could still be a critical point, and I have no recipe to find it, right? So that's why there's a distinction. Yeah. Good. So why is it, let's go to your question really, why is it hard to find critical points? Even for some simple class of non-convex functions as simple as cubic polynomials. Right? I'm going to give you a reduction from the Max-Scott problem. So let me remind you what that is. So imagine you have a graph. Let's take all the edge weights to be 1. And a cut in a graph is a way of splitting the nodes into two sets. Let's say these nodes are getting labeled -1, and these nodes are getting labeled +1. And the size of the cut is the number of edges that go from one side to the other. So this cut has value 8, and the largest possible cut in this graph has value 23. So the Max-Scott problem is, given a graph and an integer k, tell me if there is a cut of value at least k. So we can very easily model this problem as that of testing if a system of quadratic equations is feasible. So here I'm asking every node to get a label +1 or -1. -1 would be b to the left-hand side of the cut, and +1 would be b to the right. And this is saying that the number of edges crossing from -1 to +1 is k. Why? Because if xi and xj have the same label, then this vanishes. But if 1 is 1 and 1 is -1, then this term contributes a 1 minus -1. That contributes a 2. But I'm canceling that with a 1/2. I have another 1/2 because I'm double counting all the edges. So you can trust me that this system is feasible if and only if the graph has a stable set of size k. Okay. This graph has a Max-Scott of size k. All right. So now the cubic polynomial we construct is very simple. It will have, so if your graph had n nodes, this polynomial has 2n plus 1 variables. And it's really the sum of a new variable times each constraint. So it's sum of yi 1 minus xi squared plus this new variable y0 times that constraint. Right? Now notice that this polynomial is linear in y. So when I look at the gradient, and this is on the next slide, the derivative with respect to y should return this quadratic constraints. And that's exactly what happens. So I've rewritten this polynomial in 2n plus 1 variables. This is its gradient. The sum partial with respect to xi, but the partial with respect to y is giving me the Max-Scott constraints. So now let's see. If the graph had a cut of size k, so that's a plus minus 1 assignments to xi that makes these two entries vanish. So set x to be that plus minus 1 value and set y to be 0. This will vanish, and that's the critical point of P. Conversely, if there is a critical point, so if there is an x and y that make this vector vanish, just forget the y part and return the x, and that will be a cut of size k. Right? So this shows that if I could find the critical point or test if a cubic has a critical point, I could solve the max cut problem. But like Sasha asked, this doesn't necessarily rule out that finding local minima is NPR. So why is it about local minima in the case of cubics that actually makes things easier? So there is some nice geometry that happens. So this is actually a very simple theorem to state. So it turns out that the set of local minima of any cubic polynomial is a convex set. So if you have a cubic polynomial, it may have no local minima, it may have one, it may have multiple, but the set of local minima is always a convex set. And this is very special to cubics. It's clearly not true for quartics, even in dimension 1. Right? So this quartic has 2 isolated local minima. Okay? So once again, I'm not going to prove this, but let's draw a picture for some intuition. So here I have a bivariate cubic. And if you plot the set of its critical points, so these are the red lines are where the gradient vanishes, this is not a convex set. It sort of makes sense because it's some this 0 set of some quadratic equations with some structure. But now if I look at the points where the Hessian is positive semidefinite, that's the triangle here. So I claim that set alone is always a convex set. In fact, it's a linear matrix inequality, right? Because if I have a cubic polynomial, the Hessian will be a matrix where the entries are affine functions, right? Because I'm differentiating twice. I'm going from degree 3 to 1. So the x's where the Hessian is PST is exactly a spectrohedron, right? But what's really nice is that the intersection of these two sets, just like this picture, remains convex. So that would be this top line. And all the local minima have to be within this top line because they need to satisfy first and second order necessary condition. In this example, it turns out all of the top line will be the local minima, which is a convex set. And this theorem checks out. Right? Now, the proof of this theorem, which I'm not presenting, is exactly uses the characterization that I had before. We say if you have 2 points that satisfy conditions 1, 2, 3, their midpoint will also satisfy conditions 1, 2, 3. Right? So it uses this algebraic characterization of local minima for cubic polynomials. All right, nice. So we know that the set of local minima is a convex set. Now, that does not mean that this problem is now tractable, that we can check membership to this set or we can optimize over this set, because we need to have some more algebraic structure. Okay? So every time you prove something is a convex set, it's a very good next question to ask, is it always a polyhedron, for instance, right, with tractably many facets? Unfortunately, this is not the case. So here's a simple example of a cubic polynomial in 4 variables. I'm plotting the projection of the set of its local minima to 2 variables, x1, x2. And you see the projection is not a polyhedron, so the set upstairs could not have been a polyhedron. But what's nice is that if polyhedra don't always work, but spectrohedra do. So this is the main result, that the set of local minima of any cubic polynomial is semidefinite representable. So is the projection of a spectrohedron. So it could look like some of these pictures. It's always a convex set. And you can always optimize over it using semidefinite programming. In fact, we showed that the converse of this theorem is true, that if you have any semidefinite program, the feasible set of the semidefinite program is a projection of the set of local minima of some cubic polynomial. And in fact, the construction of the cubic polynomial is explicit and takes polytime. So if you give me an SDP, I can write down a cubic polynomial whose local minima correspond to the feasible set of that SDP. One corollary of this theorem, the second theorem, is that if you have an algorithm for finding local minima of cubics, your algorithm is an SDP solver. Because I can take my STP, I can write down a cubic polynomial, and if your algorithm finds a local min, your algorithm is solving my STP, right? The second theorem is, in fact, much easier to prove than the first one. The first one is the main result that the set of local minima itself is an STP. But together, the rough, and this statement is more precise in the paper, but the rough message is that complexity of semi-definite programming is exactly equivalent to complexity of finding local minima of cubics. Questions about this? Only one slide on, maybe at a high level, what's the connection to semi-definite programming, and what do local minima of cubics have to do with semi-definite programming, right? And the connection comes from sums of squares, as some of you may expect. And here I have a cartoon of a univariate polynomial, which gives the intuition. So I want to find a local min of a cubic polynomial. And if I minimize p over all of Rn, I'm going to get minus infinity. I have an odd degree polynomial. But what I'm doing instead is I'm minimizing over what we call a convexity region of p. So the region where p is convex. So in this case, that would be here, if you can see this curve. And you can see that the optimal solution to this problem is exactly a local min. So this can be formalized in higher dimensions. This statement is true. But the question roughly is, so how would we solve this problem? Because even though the feasible set is a linear matrix inequality, the objective function is not convex. It's some cubic polynomial. So the way we do this is that instead of solving this problem, we solve what I think of as an algebraic dual problem, where the decision variable is no longer x. I'm searching over some polynomial sigma, which is a sum of squares, meaning that it can be written as a sum of squares of other polynomials. I'm looking for a matrix S whose entries are polynomials, and S is an SOS matrix. So what that means is that S can be factored as a product of of a matrix R times its transpose, where the entries of R are polynomials of X. Now, the only thing you need to observe is that if a polynomial is a sum of squares, then it's non-negative for every x. And if S is an SOS matrix, then it's positive semi-definite for every x. And the first identity is imposing that P, the primal objective minus gamma, is equal to sigma plus trace of the Hessian times S for all x. So I claim that the optimal value of the problem on the right is a lower bound on the optimal value of the problem on the left. Because if you pick an x which is primal feasible, and if you plug it into this identity, the Hessian will be PSD, and SOS matrix is PSD for any x. And then the trace of the product of two PSD matrices would be non-negative. And sigma is non-negative because it's a sum of squares, so the right-hand side will be non-negative. So that means that P is more than gamma. Right? So this is what I argued is a proof of weak duality between these two problems. In the paper, we also show strong duality at the lowest level, meaning that you don't need to go up the hierarchy. So this bound will be tight when the degree of sigma is 2, and the degree of the entries of S is also 2. Now, for those of you who've seen the Lasserre hierarchy, you should think of this as a matrix version of the Lasserre hierarchy, where I'm showing you that the first level is already tight. And I should have said that the search for sigma and S is a semi-definite program, and that's well known by now that you can impose sum of squares constraints using STP. Any questions? Okay. So that's actually all I wanted to say about the intuition here. So in the last few minutes that I have, yes, Dima?
So when you showed that it's going to be hard to find critical points, the function you looked at was not bounded from below.
Yes.
Can you make an example where it is bounded from below?
That's a good question. Cubics are not bounded from below. That reduction wouldn't work, but I would not think just boundedness from below would help you, because if I just regularize with like if I make the function coercive with like sum of xi to the fourth or some high order term, I would expect that it should still be hard to find this local minima, but it doesn't follow from that reduction. Yeah. You're right that in many ML settings where people want to find critical points, they're in some training setting where the objective is least squares and is bounded from below. But I don't think that should make critical points easier. Other questions? Yes.
I guess this is a little bit of a different track. But if
Yeah.
you have a cubic polynomial and you're trying to find its local minimum, and you do something silly, like run gradient descent or some kind of Newton-like algorithm,
Yeah.
in practice, do you expect it to not find a local minimum a lot of the time? So you have.
That's actually a good question. And in fact, Jeff started a project on that. I don't know where he is because he wanted to write a new STP solver based on finding a local minimum of a cubic with something like gradient descent. It's hard to prove it works and characterizes complexity, but it's not impossible. I think it would be some sort of first order method for semi-definite programming, and it would probably correspond maybe to some already existing first order method interpreted differently, or maybe some new one, right? Empirically, Jeff has tried it, that it works reasonably well, but it's hard to prove that gradient descent on a cubic polynomial with some version of gradient descent stops in polytime. Yeah. So that's why we went this STP route, because we wanted an algorithm with like log 1 over epsilon complexity. Good. So in the last few minutes that I have, I want to tell you like how this project led to another line of work where we started designing higher order variants of Newton's method. And this part is joint work again with Jeff and with Abrar, who is a current PhD student graduating in a couple of months. Right? So let me first remind you all what is Newton's method. So I'm sure you all know it, but here it's I'm interested in minimizing a function f, and f may be too complex. And what I do is that if I'm at an iterate xk, I replace f by second order Taylor expansion around xk. So that gives me a quadratic function q. And in the next step, I move to a minimizer of that Taylor expansion. More precisely, I actually move to a critical point of the Taylor expansion. But if f was convex at the point that I started with, that critical point would be a minimizer of this Taylor expansion. Right? So the work per iteration of Newton's method is finding a critical point of a quadratic function. It's exactly finding a zero of the gradient, which is solving a linear system. So it's polynomial in the dimension, let's say n cubed. And the most famous theorem about Newton's method is that it has superlinear quadratic, it has quadratic local convergence. So that means that there is a basin around the minimizer of f, under some standard assumptions. This basin has full dimension. This basin has full dimension. And if I start in that basin, the distance to the optimizer in the next step is less than the square of the distance in the previous step. So this leads to very fast quadratic convergence of Newton's method, compared to first order methods, for instance, where that 2 would be a 1 and the method would be slower. Right? So if you work in polynomial optimization, like many of us in this room, is you very immediately ask, why would you Taylor expand just to degree 2? That seems arbitrary, right? If I Taylor expand to higher order, my model can only become more accurate, and maybe it would do better, right? And the answer is almost obvious, though, is that if you Taylor expand to higher order, how would you do the work per iteration? How would you minimize this higher order polynomial? And we've already seen that minimizing polynomials globally is hard, but even finding a critical point is hard in degree 3, or finding a local minimum is hard in degree 4. These are things that I just claimed. But there was one case that was easy, which is that I can find the local minimum of a cubic polynomial. So in the same paper with Jeff, we proposed this, what we call an unregularized third order Newton method, where the idea is very, very simple. You Taylor expand to order 3 instead of 2, and you move to a local minimum of this third order polynomial by solving this small n by n STP. Right? So it's definitely more expensive than Newton's method, no question, but the work per iteration is still polynomial. Right? And this is sort of hard to see, but because the Taylor expansion is more accurate, if you start at x0, you can see that Newton would take you here, and the third order Newton method is more accurate and would get you closer to the global min, right? In the paper, we also observed empirically some nice behavior of the basin. So for instance, this is this fractal that you see is something called a Newton fractal. This is a color coding of the basin of attraction for different local minima under the Newton's method. So there's a function with 4 local minima, and I'm giving to every initial condition one of 4 colors, depending on which of the 4 local minima it goes to under the iterations of the Newton map. Right? And for this example, we had like less sensitivity to initial conditions, and we thought this was an interesting method. And about a year or so after, Jeff proved with his student, and I'm not involved in this work, that in fact this method has local convergence of order 3. So the same result as Newton, except that the order of convergence goes up to 3. And this leads to fewer function evaluations to find the same quality point than Newton. But then the question that I wanted to address, and this is what we did with Abrar and Jeff, is what about higher than 3? So can I make this order go as high as you want while keeping the work per iteration polynomial? Right? And this is our newest paper, and I only have one slide on it, again, very high level. I want to describe to you the algorithm that achieves this. So if you have a function f that you want to minimize, the algorithm, which we call a dth order Newton method, it Taylor expands f to order d at xk. This denotes the Taylor expansion by t of degree d at xk. And then in the next step, it finds the quote-unquote closest SOS convex polynomial of degree d plus 1 if d is odd, or d plus 2 if d is even. So don't worry about the details, but essentially the algorithm finds a convex polynomial which is close to the Taylor expansion. Now, what does SOS convex mean? SOS convex polynomials are a subset of convex polynomials whose convexity has a nice semi-definite programming-based certificate. So more precisely, their Hessian matrices are SOS matrices. And the reason we are interested in them is that the task of finding this closest SOS convex polynomial can be done by solving this SDP of size n. Right? And then the next iterate will simply be moved to the minimizer of this SOS convex polynomial. And that itself can be done by an SDP of size n. So Taylor expand, find the closest SOS convex polynomial, minimize the SOS convex polynomial. So and the claims are steps 2 and 3 take polytime. So then all the work per iteration is poly. And the claim is that this is local convergence of order d. So you can indeed make the order as high as you want. Yes?
I feel like this algorithm applied to order 3 might be different than just attacking the Abtunati conditions of order 3.
This order 3 algorithm is certainly different than the previous order 3 algorithm. This is not a generalization of that. In the special case of degree 3, this does not correspond to that. Certainly, that's a good observation. That method is unregularized, and this one is doing something different. But this works for any degree. Yes. Good. And let me just end with an example to give some intuition. What happens in dimension 1? So in dimension 1, these STBs are small enough that Abrar and Jeff could actually solve it in closed form and write an explicit expression for the next iterate of at least for the degree 3 case. So in dimension 1, this is what the degree 3 algorithm is doing. There's a geometric interpretation of it. So if you think of what Newton is doing to minimize f, Newton is really trying to find the root of f prime. And what it does at iteration k, it Taylor expands f primed to degree 1. So it's the first order Taylor expansion. And it moves to a 0 of that first order Taylor expansion. This is an interpretation of Newton's method, right? And the interpretation here is that you look at f prime and you Taylor expand to degree 2. And you add a cubic term to make that quadratic function monotone. And then you move to the 0 of that cubic term. This is what this iteration is doing. So let me just show you some examples. Like this is a univariate convex function. This is x0. And this is where one iteration of Newton would take you. The yellow function is a third-order Taylor expansion after plus a term that makes this SOS convex. So this is an SOS convex polynomial which closely approximates the function. And after one iteration, you see that we're closer to the minimizer. If you compare the size of the basin of attraction, this goes up with the degree. So the larger the basin, the size of the basin is larger. The second example shows that even in the strongly convex case, this higher order methods can do better. So Newton's basin is about plus minus 2. The basin already for the degree 3 method is all of R. And moreover, even if you start with a point that is in the basin of both, this is a plot of error versus iteration, the third order method can be considerably faster than Newton. OK, so let me end here. I guess the main message of this talk was that if you think of a non-convex optimization problem with multiple local minima, and you ask yourself, is it any easier to find a local min than a global min? I guess the message that we learned from polynomial optimization is that that's a delicate question. It's not obvious that this should be the case. So for quadratic programming, even finding points within exponential distance of local minima is as hard as finding global minima. But in some other cases, like cubic polynomials, this can be done, not for trivial reasons, but in this case with semidefinite programming. Now, methods that find local minima of polynomials can be used to design higher order Newton methods. So that was the connection between the first and the second part. If you're interested, the 3 topics I talked about are in these links. Thank you.
So the higher order Newton, is there like an analog of self-concordance?
Analog of?
Higher order self-concordance, like a class of functions for which you can prove that these algorithms converge globally?
Globally, good question. So,
can you just repeat?
Yeah, he's asking if there is, if just like Newton can have global guarantees under stronger assumptions like self-concordance, can you prove global convergence of these algorithms? So that's a very good question because you sort of see already, even with strong convexity, Newton may not be globally convergent, but there are analogs that are. So our paper has a section on global convergence, and the assumption there is that the Hessian is positive definite everywhere, and there is a Lipschitz assumption. So, which I don't remember exactly. I think that so we have a section that for degree, and I think it only works in the degrees odd, so 3, 5, and so on, is not self-concordance, but we have a section on global convergence under positive definiteness of the Hessian and a certain Lipschitz condition. Yeah. Actually, it's a good question. What happens on the self-concordance? It's not clear that if Newton converges, it's not clear that the basin of Newton should always be a subset, right? Because this is a more aggressive method. Like, in fact, there are examples, like I didn't show you, but this is a non-convex example in dimension 2. It's something called a Beal function, is a benchmark problem usually in polynomial optimization. This is the basin of Newton. This is the basin of the third order Newton. So it's larger in volume, but there's no inclusion relationship. So I don't know what happens for self-concordant functions, whether these higher order things converge globally.
So I was curious about the informally stated equivalence of cubic
Yeah.
organization in STP.
Yeah, you want me to make it more formal?
Well, I wanted to ask, are your reductions strongly polytope?
Strongly polytope, meaning that.
If you care about the bit size of the input, that it doesn't get too large when you produce.
Yeah, no, that's a good question. So let me go to this. Right. So here, one of the main open questions of complexity for semidefinite programming is whether STP feasibility in the Turing model is in P, or even in NP, that's not known, right? So there's an exact equivalence here, meaning that we show it in both directions that if STP feasibility is in P, then the problem of finding local min is in P, and vice versa, right? So yes, and there are, just like you can have STPs whose only feasible solutions are irrational, even though they have rational input, You can have polynomials with rational coefficients whose only local minima are irrational. You can have STPs whose feasible solutions have exponentially large bit size. You can have the same things with local cubics. But the answer to your question is yes, that if you could solve one, you would solve the other.
So,
Yes, I just had a question about if you go back to slide 18 to your
18?
Yeah, 18. So what happens? So if you replace in the constraint
Yeah.
the lower bound by say a multiple of identity, and you consider all the duals as vary. So if you assume that you have a lower bound of the curvature, and you consider the corresponding duals, can you say anything on this family of duals? So instead of taking the square derivative of p of x larger than 0,
if you put identity, then you may lose on the local minimum.
Impose a lower bound. You would impose a lower bound
On the curvature?
Yeah, right.
So here you put identity.
You would put some constant.
Which is negative or positive?
Positive.
But then you would miss out on the local minima, right? Because at the local minima you have, right? You would require a strict positive curvature, right?
Oh, so you would miss out on all the minima.
Potentially. Okay. So if you have a strict local minimum, right? So we know that if the Hessian is positive definite, then the gradient vanishes. You have a strict local minimum.
Right.
The converse is not true. For instance, for like x to the fourth has a strict local minimum, but the Hessian is not positive definite, right? For cubics, a point is a strict local minimum if and only if is Hessian is positive definite, and the gradient vanishes. That's a theorem in our paper. But if your cubic has local minima but does not have strict local minima, you would miss it if you do what you're suggesting. And if it has strict local minima, if your constant is too large, you may still miss it.
Let's take one more question.
So you know there are these papers on regularized cubic.
Yeah, by Nesterov.
Right. So there, right, the quadratic problem sounds like a quadratic, but plus a third power of the norm. So it's not a cubic polynomial. But there, I think, like if you apply gradient descent in a funny way, that is going to solve that polynomial.
The subproblem?
I think so.
Yeah, that's a good question. We're aware of the literature. In fact, this question that we were solving here was whether you can make this degree large and keep the work per iteration poly was posed by Nesterov. So in the case of degree 3, Nesterov has already solved this. So now we have like 3 algorithms, the one with Jeff, this one, and Nesterov one in the case of degree 3. But there's work of Nesterov and Polyak on cubic regularization, which is you do second order Taylor plus a cubic regularizer. So that's not in this framework because I consider that still a second order algorithm because the Taylor expansion is to order 2, right? But he has a paper where the Taylor expansion is to order 3, right? And then he adds a regularization to make it convex, and he solves that subproblem with something like gradient descent, some version, and he formally proves his polytime. That is correct, but there is nothing of higher order.
I think he also assumes convexity in the function.
He does assume convexity, and he assumes knowledge of the Lipschitz constant, so we don't assume those things. Yeah.
Okay, maybe we can have the rest of the questions offline. I'd like